Bro, did you see this? Like they threw the tarps and they back out and they had like their shoes like this far up.
Yeah, it's pretty slept-full. How much tarp was it?
Slow.
Was it only the rest? No, I saw that.
It's like the
Slammed it.
purple, like pink and yellow.
Yeah, they slammed it for.
Right.
Oh, yeah. That's ETS.
Sorry, Dr. Train.
Oh, no worries.
Yeah.
I'm chill. You guys are chilling.
Yes.
Oh, white test.
Oh, that's cool.
Yeah.
The one that looked like Monster Jam.
Yeah.
The shock mount that's on you got. It's so crazy.
What's the factor say to you?
It's gotta get 20.
I don't think it's
Is there a class right now?
Yeah,
let's keep going. Oh, yeah.
Not best or not, I go 401.
They must have been really constrained by those jobs.
Like, oh, we're getting for that.
Yeah.
That's another thing.
Yeah.
I'll let you guys know.
Alright. Testing.
Oh, he transferred?
You're supporting.
They have free training.
That's free.
I can run my. Like the. They didn't say anything about how
They just wanted to see FDA, like in pictures, but they really wanted to see like how you tested it.
Yeah, they didn't care about math lab. How are you?
Good. How are you? You guys had competition last week, right? How'd that go?
Got back.
Oh, really? Dang.
It's been a long week
Oh
out in Arizona. And
my goodness. Did Dr. Miral go with you guys?
Yeah, Dr. Merrill and John went with us.
Oh, nice. That's awesome.
It's good. Quite the learning experience.
I bet.
Never know what you're gonna expect sometimes.
Forgot once.
Hey, Dr. Tran.
Hey, guys.
Good afternoon. Troy says he wants a really hard final. Travis said he wants you to give him the AP level. Yeah, I don't technically all four exam. He wants you to give him the 500 level.
Maybe I'll get forming on use your final because they won the bigger award last Friday.
Otherwise, we'll all have an asterisk saying best legacy.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. All right, so we're in our last week. So this week is mostly just kind of clean up and just review for the final. So we're not doing too much. Today I mostly just have, we started an example last Thursday. So I wanted to finish that up first thing today. And then we're going to go through our very last topic. It's a short topic about environmental radiation balance, which is kind of the last thing you're going to need to know for the final. Okay. So we should finish up today. I have no doubts we'll finish up everything. And so by Thursday, we'll have basically the entire time for just review. So what I'm going to do today is I'm going to put a poll out on Canvas, and I'll email everyone with the poll. And I want you guys to vote on the topics that you want to see reviewed in the review session on Thursday. Because we're not gonna have time to cover absolutely everything in just one lecture. So I want to just make sure to focus it on the topics that you guys want to see. Because typically what I do is I'll review the important concepts. I'll maybe do just one quick example. We'll probably be able to cover the top 2 topics on that, from the list of topics that I have that I send out. Okay. So make sure, just keep an eye out for that email later today and make sure you vote on that before Thursday. And then we'll review the stuff on Thursday. Okay. All right. And then remember, our final exam is going to be next Tuesday. So that's May 13th. It's going to be in here from 1 o'clock until basically 3 o'clock. Okay. All right. Any questions, anything before we begin for today? Okay. All right. So let's go ahead and get started. So actually, first thing I'm going to do is I'm going to go back to the lecture notes from last Thursday. Because we are right in the middle of doing this example here. Okay. And so, you guys should all have this written down. So I'm not gonna spend too much time on this. But basically, we want to compute the radiation exchange between these 2 parallel plates. Okay, so we have plate number 1, plate number 2. And the big difference about this problem compared to the ones we've done before is that both of these plates are considered gray bodies. So you can see here that plate 1 has an emissivity of 0.8. And plate 2 here has an emissivity of 0.6. Okay. And so, last Thursday, we kind of introduced the idea of, how to, deal with these, but now we're going to do an example, just kind of put it all together. Okay. And since these 2 plates here are connected by, there's space in the middle, we are going to create kind of a third pseudo surface, which we call surface 3. Okay. Just so that we can have an enclosed space. And that one, we're going to treat it as a black body. So we're going to assume this one has an emissivity of 1. Okay. So when you have these gray body radiation exchange problems, there's typically 3 things that you need to do. So first of all, you should draw the thermal circuit. And so, that's going to represent the heat transfer in this situation. You'll see that these circuits are a bit more complicated than the ones we've dealt with before. So it's important to draw it just to help visualize how everything is. Step number 2 is to compute all of the relevant view factors. And then step 3 is to solve for the radiosities, okay? And then, if there's any step 4 after that, once you have the radiosities, you can then use those to compute heat loss from each plate to the environment, okay? But typically for these radiation exchange problems, these are the 3 steps that you need to follow. And in fact, I'm just about done writing the final exam. The problem on this in the final exam is we're just going to go write down 1, 2, 3, just like this, okay? Okay, so here's our thermal circuit, all right? So the thing to note with the thermal circuit, so actually let's do this. Let's redraw the thermal circuit because I think that'll be kind of helpful to do. Okay. 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 Because in a lot of sense, the radiation thermal circuit is kind of sets the baseline for these problems. So if you don't draw the thermal circuit correctly, it's going to mess up all the other parts of the problem here. Okay. So the thing to remember when drawing a radiation thermal circuit is that, remember that radiation can, as long as you're able to see another surface from another one, then there's going to be a resistor connecting those two. Okay, because remember, when you have radiation happens equally in all directions. So as long as there's a line of sight basically from one surface to another, then you have to consider radiation exchange between those surfaces. Okay. And so what you're going to see from this is that, compared to our previous thermal circuits where, previously our thermal circuits were just a straight line, basically. So heat only traveled in one direction. For a radiation thermal circuit, what tends to happen a lot is that you're going to have a lot of branching paths because one surface can radiate onto maybe 2 or 3 different surfaces in the problem. Okay. Right. So don't be alarmed if your radiation thermal circuit is quite complex. It's supposed to be. Okay. Okay. The other thing I want to kind of highlight that, that was, we talked about it last Thursday, but, if you have a surface in your problem that's considered as a black body, then in those cases, you can ignore the thermal resistance associated with its emissivity. And essentially what that means is that for any black body surface in your geometry, then you do not have to compute its radiosity. Okay. So let me show you what I mean by that. So let me go ahead and draw the circuit again. Okay. Or let me draw the figure again. So our figure for this problem looks like the following. So we have 2 parallel plates forming basically a radiation sample, I guess you could say. All right, so we have surface 1, surface 2. And then we have kind of the this pseudo surface that we're drawing in between them, which we're calling surface 3. Okay. So with 3 surfaces in this problem, let's go ahead and start with drawing our 3 nodes. Okay. So we're going to draw end nodes for surface 1, surface 2, and surface 3. Okay. And I will try to make it as close to the figure as I can. So let me draw node 2 up here. I'll draw node 1 on the bottom. Okay. And then node 3. I know node 3 kind of encompasses two different, sides there, but we're kind of lumping them together as one because they are the same temperature. Okay. Okay. Now for surface 1 and surface 2, we need to draw in the gray body resistance for these ones because they have or they have an emissivity that's less than 1. Okay. So we have R1 is equal to 1 minus epsilon 1 divided by epsilon 1 A1. Okay. And then for surface 2, we have R2, which is 1 minus epsilon 2 divided by epsilon 2 A2. Okay. So we have to draw these resistances for these two surfaces because they are gray bodies. Okay. But since surface 3 is a black body, okay. So in other words, it has an emissivity of 1. So we said, if you go back to the figure from the last problem, we know that emissivity 3 is equal to 1.0. Okay. So when you have an emissivity of 1.0, that means you can neglect the gray body resistance. Okay. And so there's no additional resistance that we need to draw there. Okay. Okay. So that's how you should start your circuit. So whenever you're first drawing your radiation circuit, start with all the end nodes and then draw in the gray body resistance for the surfaces that are gray bodies. Okay. All right. Any questions on this so far? Okay, good. All right. So the second step to drawing your radiation circuit here is to add in the radiosities. So for every surface that has a gray body resistance, we're going to put a radiosity on the other side of the resistance. Okay. Right. So that's going to be J1 right here and J2 up top here. So for all gray surfaces, include a radiosity. Okay, so for every surface with the gray body resistance, we need to include this radiosity on the other end, right? So our radiosities are J1, J2, and remember these represent, basically it accounts for the fact that these surfaces can also reflect radiation as well as absorb it and emit it. Okay, so that's kind of what those two represent. And since these surfaces have non-perfect emissivity, then there is going to be some reflection that takes place. Okay, good. All right, so after we draw in the radiosities, the last thing to do is to connect all of these surfaces together, okay? So basically, we're going to make every combination here possible. So from node 1, we need to connect node 1 to node 2. Okay? So that's going to be R12. And then we need to connect node 1 to node 3 as well. So we're going to have one resistance that goes like that. That's going to be R13. All right, and then the only other combination we have there is node 2 and node 3. So we need to connect 2 and 3, just like that. Okay. And this is going to be R23. All right, and so all these resistances that connect the different nodes are different surfaces. These are view factor resistances. Okay. So R12 here, this is going to be 1 divided by A1 F12. Okay. R13 right here is going to be 1 over A1 F13. And R23 is going to be 1 over A2 F23. Okay. Question, yes.
Can I see the surfaces?
Yes. Yes, we have two parallel plates here, and then we've created kind of a third surface that just to make an enclosure with these two.
And then also for the circuit that we built,
Mhm.
are there different ways that we could draw it, or is that the only way that we could draw it?
You can definitely draw it different ways. And so, I drew it this way just to make it easier to kind of visualize, but as long as you have the same connections, so you still have, 2 is connected to 3, 1 is connected to 3, 1 is connected to 2, you can arrange these resistances in any way that you want. Yeah. Mhm. Yeah, the circuit is just there to help you kind of visualize where the radiation heat transfer is going. So, if you draw the diagram a bit differently, as long as all the connections are the same, then it's fine. Mhm.
Thank you.
Yep. All right. Any other questions on this circuit here? Okay, good. All right. So this circuit is nice here because not only do we are able to kind of visualize and see that surface 1 can go, heat can go from surface 1 to surface 2. And if it's going to do that, it's going to cross this resistance here. Okay. But we can also see that heat can also go from surface 1 to surface 3. And that's going to go in this direction. Okay. And then same thing from 2 to 3 as well. So this is Q2, 3. Okay. So the resistances are there to basically show you the different paths that heat can go. And when you have kind of a complex system like this with a lot of different surfaces, it's good to kind of visualize all of this. Okay. And the gray body resistances are meant to represent the fact that, these surfaces are not perfect emitters. And so when you go from the N node over to J1, there's still going to be some resistance that it experiences there. Same thing as you go from N node 2 to radiosity 2. Okay. Because the non-perfect emissivity, you can essentially think of it as adding additional resistance to heat transfer. Okay. One last thing about the circuit that I forgot. So for each of the N nodes here, the value of the node at those points is going to be equal to its black body radiation. So for node 1 right here, we're going to say this is the nodal value here is going to be sigma T1 to the 4th. For node 2 up here, it's going to be sigma T2 to the 4th. And node 3 is going to be sigma T3 to the 4th. Okay. That's going to play a role once we compute the radiosities. Okay. All right, good. So we have our circuit here. Our next step in this problem is to make sure that we can compute all the values of all the resistances. Okay. So usually when you're given a problem like this, usually, you are usually given all the emissivities. So epsilon 1, epsilon 2, those are usually given to you. Okay. Most of the time, you're going to be given the geometry in the problem as well. Okay, so the geometry is going to let you compute A1, A2, A3. Okay. And so the next step and the final step that you have to take to compute all of the resistances in this problem is to compute the values of all the view factors. Okay, so that's F12, F23, and F13. Okay. So let's go ahead and do that. So next step after we have our circuit is to compute all of the view factors in the problem. Okay. All right, so let's list out all the view factors that we need from the circuits. We need F12, we need F13, and F23. Okay. All right, but of course, these are not the only view factors that we can get, because remember, you can also compute the reciprocal view factors as well. So you can also compute F21, F31, and F32. Okay. So technically, there are 6 view factors in this problem, although we don't need all 6 to complete our circuit. So usually you only have to compute a subset of the view factors. Okay. But you know, usually it doesn't hurt to compute all of them if you can. Okay. Okay, so let's go ahead and do this. And so you know, we've computed view factors before. And so in this problem, we're not given any view factors, and so we're going to need to compute them from scratch. Okay. And so since we're not given any view factors, okay. And for this problem, you know, there's not enough information in the diagram itself to find one via inspection. So, you know, there's no symmetry or there's no inspection that we can take advantage of. Okay. Then our only option here is to use a table to at least compute one of the view factors. And then based on that value, we're going to compute all the others, either via reciprocal rule or summation. Okay. Okay. And so from the table, right, for this particular geometry, we do have a table value that is convenient. And so for two parallel plates, okay, and so this is from a table. I don't know exactly what table it is in the textbook, but also you won't need this for the final. And so I'll go ahead and tell you guys now. So I know you can probably find this table in the textbook or online, but you're not going to need it for the final. You don't need to put it on your cheat sheet. Okay. So what I'm going to do on the final exam, I'm going to give you one or two of the view factors, and then you're going to compute the rest of them via summation or reciprocal property. And so I'm showing you the table now just because we need it for this one, but for the exam, you're not going to need this formula here. Okay, so for two parallel plates, let me go ahead and draw the diagram. Okay. And so this being L1, this being L2, and the separation between them being H, okay? And so for the view factor between surface 1 and surface 2, so F12, from the table, we have this formula here. So we have square root of L1 over H plus L2 over H quantity squared plus 4, okay, minus square root L2 over H minus L1 over H quantity squared plus 4, all divided by 2 L1 over H. Okay. Yeah.
The view factors be given on the exam, or do we need to have a list?
So you won't need the table, but what's going to happen for, you know, for any given problem, there's always going to be 3 or 4 different view factors you need. So I'll probably give you 1 or 2 of them, and then you're going to need to compute the others via summation or reciprocal rule.
Because yeah, you could just reverse some.
Exactly.
Thank you.
Yeah. Okay, so if you plug in the numbers for this problem, what you're going to get is F12 is equal to 0.414. Okay. So on the exam, you know, you'll probably start from here. So, you know, I won't give you this formula here, but I'll just tell you straight up in the problem that the view factor between surface 1 and surface 2 is 0.414. And that's going to be up to you to find the rest.
Thank you.
Yeah. Okay. All right, but now that we have this, we can compute the rest of the view factors either by summation rule, mostly summation rule, or the reciprocal rule. Okay. Okay. Okay, so let's start. Let's start with F13. So let's use the summation rule to find F13. Okay. All right, because we know that if we sum up all the view factors that involve one particular surface, right? It has to equal to 1, right? So every view factor that involves surface 1, if we add them all up, it's going to equal to 1, okay? All right, so what this looks like is that if we add F11 to F12 to F13, okay? So that's every single view factor possible involving surface 1, then all of this has to sum up to 1, okay? Now we know F12, we just computed it, so we know F12 here is 0.414. Okay. So that's something that's either going to be given to you or it's something that you can compute using a table. For the exam, it's something that's been given to you. Okay. And we actually already know what F11 is as well. Remember, F11 here, that's the self-view factor. Right. So that represents the capability for a surface to radiate on itself. Okay. Now, but since surface 1 here is a flat surface, it's impossible for it to radiate on itself because it's completely flat. Okay. So the self-view factor here is going to be 0 since surface 1 is flat. Yeah.
So, for the self-view factor, when it's equal to 0, is it just like the plane itself, or does the angle matter?
The angle doesn't matter. So the plane itself just has to be flat.
Like the whole problem we had in V, that would also be self-view
Exactly.
factors.
Exactly. Yeah.
You said the view factors are independent of effect on whether or not they're black or gray body, is that correct?
Correct. Yes. So the view factors are purely just based on geometry situation. So it doesn't matter if they're black body or gray body, the view factors are going to be the same. Yeah, good question. Okay, and so if we plug everything in here, oh, excuse me. So surface question from the chat. So what type of surface would be able to have a view factor on itself? Yeah, that's a good question. So typically a surface that can radiate on itself are going to be concave surfaces. And so, you know, if we had a surface that looked something like this, right? And so if all of this was considered one surface, then what can happen is that, you know, radiation can leave this part of the surface and then just hit on itself right there. Yeah, parabola would be a good example of that. Basically anything that's concave could radiate on itself. Now, another really interesting case is when we draw kind of these imaginary surfaces as well. So actually there is a surface in our problem here that can radiate on itself. And so if I draw the geometry here again, right? So this here's surface 1, surface 2, right? Remember we drew kind of our phantom surface here 3, and we used it to kind of encapsulate both ends of the plates, right? And so since we're kind of lumping together those two side kind of phantom surfaces together, F33 here actually is not going to be 0 because it is possible for radiation to go from here and hit itself over there, right? So radiation has to go out from a surface and it can only travel in a straight line. And so if you're not sure if the self view factor is going to be 0 or not, just, you know, draw some straight lines coming out from the surface And if it's possible for those straight lines to hit the surface again, then the self-view factor is going to be non-zero there. Question, yes.
Are you able to take a different approach and call that phantom surface 3 and then call the other one 4?
You could do that too. Yeah.
Are there benefits to that or?
Sometimes, and so you know, if you were interested in computing, you know, how much radiation goes off to the left, to the right, that would have advantages in that case. But in this case, most of the time we're only interested in how much is totally lost to the environment. And so in that case, it's a bit simpler to combine them. Because if you add another node, right? So if you add another surface, that's going to add another node to your circuit, and that's going to make things a lot more complicated. So yeah, most of the time it's better to lump it, especially if they're all at the same temperature. But you know, there could be reasons where you'd want to separate them as well. Okay. Yeah. All right. So in this case, F33 is not zero, but F11 and F22 are both equal to 0 in this case. Okay. Okay. And so if we plug all that in, we can finally solve this for F13. And so we have F13 is equal to 1 minus 0.414. And so we get F13 is equal to 0.586. Okay. All right. And then the other one that we need for our problem is either F23 or F32. Okay. Okay. All right. Question, yes.
I mean, as you said, it would be a self-view factor if it's concave.
Yep.
So then, but that also is applied to this case because it's two
Exactly.
plates coming at each other.
Exactly. Yeah. Yeah. So if you're not sure, just visualize. So draw the lines
It'd be
and
like
see.
deflecting off and then come back to itself.
Well, it would be emitting from one surface and then hitting itself again, basically.
Okay.
Yeah. Yeah. Question.
On the homework, you were talking about a bin,
Mhm.
there's like a sharp edge.
Yeah.
And are we able to consider those two different surfaces? Or-
Most of the time, yeah. Most of the time, you're going to consider them as two separate surfaces.
Okay.
Yeah.
Thank you.
Okay. Let's do F23. So we don't have a straightforward way to get F23 here. We're going to have to come at it from kind of an indirect way. So first thing, let's apply our summation rule. Because we know that if we apply the summation rule for surface 2, we know that F22 plus F21 plus F23 is equal to 1, right? We know F22 is equal to 0 because it's a flat surface and it can't radiate on itself, right? And so we have F21 plus F23 is equal to 1, okay? Unfortunately, we know neither, and so we can't we can't say anything about that. But you know, there is a quick way that we can solve for F21, right? Okay. Now there's I would say kind of a very easy way if you're kind of observant to compute F21. But there's an actual, mathematical way to compute it as well. Let me show you the mathematical way first. And so the mathematical way to solve for F21 is to use our reciprocal property. Okay, because we know that A1 F12 is equal to A2 F21, right? So if you're just going to swap the two indices on the bottom, then you can relate them using the reciprocal rule. Okay, and so from this equation, we can see that F21 is equal to A1 divided by A2 multiplied by F12. Okay, or A1, A2 here, that's the surface area for each of those plates. Okay. So surface area, how are we going to compute that? Well, surface area, right? If we consider this to be L2 and this to be L1, right? And kind of what we're implicitly assuming here is that, both of these plates have the same depth going into the page, right? And so this distance here will be D. This distance here will be D. Okay. Usually that's the case in these problems. I think that your homework problem is the same where, I tell you that there's a uniform depth into the page. And so in this case, the ratio of the areas is going to be L1 times D divided by L2 times D. So A1 over A2 here is going to be L1 times D divided by L2 times D. Okay. And we're going to multiply that by F12, which we already know. We knew that from before. Okay, so our two depths are going to cancel out. And so we just have the ratio of L1 over L2, okay? And it turns out in this problem that L1 and L2 are also exactly the same. Okay, so since L1 is equal to L2, then what we get is F21 is equal to F12. Okay, so they're both exactly the same. All right. So that's kind of the mathematical, kind of the real way to kind of solve for this. If you were observant, what you can say is that, L1 and L2 geometrically are exactly the same from each other, right? They're the exact same length and they're separated by the exact same distance. And so just by inspection, you can come up to the same conclusion. Okay. And so since L1 and L2 or plate or surface 1, surface 2 geometrically are exactly the same, especially with its relationship to surface 3, then you didn't have to go through the whole reciprocal rule. You can just say that just by symmetry or by inspection, we know that F21 has to be equal to F12 because they're two plates, they're parallel to each other, they are the exact same length, and so they have to be the same. Okay. Okay. And so now that we've established that F21 is the same as F12, we can come back up to our summation rule up here, okay? Now that we know F21 here is 0.414, same as F12, okay? Then we know that F23 has to be equal, well, it ends up being the same thing as F13, which is 0.586. Which you could have also gotten by inspection because plate 1 and plate 2 are both geometrically the same. That means they're going to have the same relationship to surface 3 as well. So that means their view factors with relation to surface 3 should also be the same. So F13, F23, the same in this case, just because of the symmetry. Okay. All right, question. So are there scenarios where we can't use the reciprocal, like certain conditions when we need to use it? I can't think of any. So reciprocal rule should always be valid. And so as long as you have two surfaces and you can compute both of their surface areas, the reciprocal rule is always going to be valid. And so this equation, I don't think there's any situations where you can't use this. So this is always kind of a safe bet to use. Yeah. Same thing with summation rule too. All right. Any other questions on this part of the problem here? Okay, good. Okay, so now that we have our view factors, and so, we only needed 3 of them. And so we only needed F12, F13, and F23, okay? So since we have all 3 of these now, we can compute all of the resistances in our circuit, right? Okay. And so you compute the areas, we know the emissivities, we have everything we need to compute the circuit. And so we're finally ready to move into the last phase of the problem, which is solve for the radiosities. Okay. So we did this last Thursday, so we know kind of how to do this. But basically what we're going to do here is we're going to set up a system of linear equations to solve for the radiosities based on the rules of the thermal circuit that we drew. Okay, so for this particular problem, we have two gray surfaces here. So there are two radiosities we need to solve for. So that means we're going to need to we need to derive two equations here to solve for the radiosities. Okay. Okay. All right, so let's go ahead and do that. So let's go back up to our circuit. And remember, the thing that the technique that we're going to use here to solve for the radiosities is to basically sum up all of the heat that's going into a particular node and subtracting all of the heat that's leaving a particular node. Okay. So let's start with the J1 node. Okay. So let me go ahead and circle J1 right here. Okay. And so we need to quantify all the heat that's coming in. So all the heat that's coming in is going to come from usually from the N node. Okay. And then we need to set that equal to all the heat that's going out. And so once the heat arrives at J1, it can go two directions. And so it can either go to surface 2 or it can go to surface 3. Okay. So this is going to be Q12 and this is going to be Q23. Okay, so let's set up our equation with that in mind. Question, yes.
And you mean Q13?
Q1, yes, thank you. Thanks for catching that. Yep, so it's going to be the heat from node 1 to node 3. Okay. All right, so let's go ahead and set up our J1 equation. Okay, so our J1 equation is going to look like this. And so we're going to have Q in coming from node 1 is equal to Q12 plus Q13. Okay. So basically all the heat coming in is equal to all the heat coming out. Okay. And remember to compute a Q, all we're going to do is we're going to take a difference between the two nodal values divided by the resistance in between them. Okay. So for Q in, this is going to be equal to sigma T1 to the 4th minus J1 divided by the gray body resistance in between them. And so that's going to be 1 minus epsilon 1 divided by epsilon 1 A1. Okay. All right. And then let's go ahead and quantify the heats coming out. So Q12, right? This is the heat transfer from surface 1 to surface 2. So it's going to be J1 minus J2 divided by the view factor resistance between them. So that's 1 divided by A1 F12, okay, plus Q13. So that's going to be J1. Remember, surface 3 is a black body, so we don't have any radiosity for surface 3. So that's going to be minus sigma T3 to the 4th divided by 1 over A1 F13. Okay.
What is epsilon again?
Epsilon, that's our Boltzmann constant. So epsilon is 5.67 times 10 to the minus 8 Boltzmann. Yep. All right, so now that we've computed all the view factors, we are able to compute everything in this problem here except for J1, J2, okay? So if we plug in and simplify, right? All right, so after you plug things in, you're going to see that there are some common factors that you can combine. So all the J1 terms you can combine together, all the constant terms you can combine together. So there is a bit of algebra that's involved in this, but after you plug everything in, what you get is 93,166.41 is equal to 5J1 minus 0.414 J2. Okay. So you can see we have one equation and we have two unknowns. And so in order to solve for J2, we need a second equation that we can solve together with this one. But are there any questions on how we set this one up here? Okay, good. All right, so let's do the same for J2. So let's go ahead and set up our J2 equation. All right, so we're going to set it up in the same way. So this is going to be Q in from node 2 is equal to Q21 plus Q23. Okay. And so once again, you're going to have to go up to the circuit to find these out. But just in the interest of time, let's go ahead and write this down. So Qn2 is going to be sigma T2 to the fourth minus J2 divided by 1 minus epsilon 2 divided by epsilon 2 A2. Okay. So that's the view factor resistance from from surface 2, or excuse me, the gray body resistance for that. All right, Q21, this is going to be J2 minus J1 divided by 1 divided by A2 F21, okay, plus J2 minus J3 divided by 1 over A2 F23. Okay. All right. Oh, sorry, J3 here, this is sigma T3 to the 4th, because it's a black hole. Okay, all right, so let's go ahead and plug everything in. You're going to see that the only unknowns in this situation are J2 and J1. So after we plug in and simplify, all right, so we do that and we get the following equations. We get 11,291.61 is equal to 2.5 J2 minus 0.414 J1. All right, so now that we have two equations, we can use them to solve for our two unknowns. And so we can use these to compute J1 and J2, okay? Now for the exam, solving a system of equations like this, I've tested it pretty extensively. It is very time consuming to solve for these equations. So I'm not gonna have you solve these equations in the exam. What I am gonna have you do is set up these equations, and then that'll be the end of the problem.
The final, it's cumulative, right?
It is, yes. Yeah, so definitely check the study guide because it's not absolutely everything this semester, but it is a smaller list. But there is stuff from the first midterm. Question, yes.
So once we have the general solutions in blue, we still have to simplify it down to the numbers, right?
Yes, yeah. Okay. But in theory, you know, once you have these two equations, you can solve them simultaneously. You can use a substitution rule to solve for J1 and J2. Okay. Any questions on this before we move on to our very last topic?
Yeah.
Yes.
So for the summation rule, the reason why it's equal to 1 is because you're trying to balance the circuit.
No, so it's equal to 1 because remember the view factors represent basically the percentage of radiation that goes from one surface to another. And so whenever you have an enclosed system where basically everything is, there's a closed loop,
Right.
then all the radiation has to go somewhere. So it's impossible, you know, for this box, right? It's impossible for radiation to not hit, you know, if you're looking at surface 1, right? The radiation either has to hit surface 2 or it has to hit surface 3. There's just nowhere else for it to be. And so that's why the view factors, they sum up to 1 when you have an enclosure. Yeah. Mm-hmm. All right, any other questions on this? Okay, all right, so the very last topic that we're going to cover, there's no problems associated with this. It's really just conceptual. But we need to talk about what's called the atmospheric radiation balance. Okay. All right, so I've put this in the radiation chapter, mostly just because it's part of the radiation chapter in the textbook. You know, but it concerns, you know, probably the most important source of radiation that we get every day, which is from the sun, right? Okay. So now that we're familiar with the concepts of radiation and we have an idea of how it works, we can actually start to put some numbers in terms of, you know, how much heat the sun actually sends out. Okay. So, you know, of course, there's a lot of debate on this because, you know, no one's been to the surface of the sun. But there are estimates. Okay. And so usually just for the sake of calculations, we assume that the sun is a black body, which is kind of weird to say because the sun is very bright, but you know, from its radiation properties, from our perspective, it has perfect emission and perfect absorption. Okay. And we have an estimate of the surface temperature of the sun. And so the sun's surface temperature has been estimated. And so this is as of, I think I wrote these notes in 2019. So as of 2019, the surface of the sun was estimated to have a temperature of 5,800 Kelvin, which is impossible to kind of, you know, conceptualize just because, you know, there's nothing near that hot on planet Earth. But the sun has to be really hot in order for its radiation to reach us, okay? Because if you think about the amount of distance between the Earth and the sun is, it's very large. And of course, it depends on what season it is and what you know, what part of Earth's orbit that we're in. But on average, you know, the distance between the Earth and the sun can be approximated to 1.5 times 10 to the 11th meters. Okay, so the radius from the sun to the Earth is about 1.5 times 10 to the 11th meters. Okay. And so even though the sun is insanely hot, you know, it is very, very far from the Earth. And so, you know, we're not blasted with, you know, 5,800 Kelvin degrees, you know, because we are very, very far. Okay. Not only that, another thing that limits the amount of radiation the Earth receives is the fact that relative to the sun, the Earth is extremely small. Okay. And so what that essentially means is that the view factor, if you were to compute one, if you were to compute the view factor from the sun, between the sun and the earth, it's probably, really, 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 really small. Right? So only a very, very small percentage of the heat that comes off the sun actually reaches the earth, which, I think everyone's familiar with that already, just knowing how far the sun is. But I think it's fun to kind of put some numbers on this and put it into perspective of kind of what we've been talking about so far with radiation. Okay. Okay. So with all that in mind, a convenient way for scientists to actually quantify how much heat flux enters the earth or hits the earth is to use something called the solar constant. Which is not a measurement, but it's kind of the theoretical maximum of how much radiation from the sun will hit the earth. So basically, the way that they computed the solar constant here is they just did a very simple geometric radiation problem. So they stuck, they literally stuck a rectangle that's roughly the size of Earth, or roughly the same distance from the Earth to the sun, and they found out how much heat hit that really tiny rectangle. Okay, and so the solar constant is equal to 1,368 plus or minus 0.65. In my opinion, it's kind of ridiculous to have kind of a plus or minus here because there's so many assumptions here. You might as well just state it. But 1,368 plus or minus 0.65 watts per meter squared. Okay. So that's a theoretical maximum that the of heat flux that the Earth receives from the sun at any given time. Okay. But of course, the actual amount of radiation that the Earth receives is not actually this. And then, if you consider the fact that the Earth is rotating as well, then the amount of radiation that we receive on any given day is going to be much less because, for half the time, the Earth is going to be turned away from the sun. Right? Okay. Right. Not only is there rotation, but also the Earth is not a perfect absorber either. So actually, a lot of the sun's radiation actually just bounces off the Earth and reflects back as well. Okay. Okay. And so the actual number that scientists typically work with is 342 watts per meter squared. Okay? So the actual irradiation, so we call this GSO. Okay? So that stands for solar irradiation, is around 342 watts per meter squared. Okay, so that's the actual amount of radiation that enters the atmosphere, you can say. Okay. Now, why is this number important? Well, you know, we've kind of spent this whole entire semester, you know, talking about heat exchange in kind of smaller systems, right? But if you consider kind of our Earth's atmosphere and our Earth's environment as kind of one big thermal kind of, you know, capacitor or thermal kind of storage unit, then knowing how much solar radiation is coming in is important for us to know, you know, if heat's getting trapped here, if enough heat is leaving. And so all of this kind of has to do with climate change, global warming, you know, and now that we're kind of at this stage in the class, you know, we're kind of ready to kind of, you know, quantify some of these things and talk about some of these concepts that lead to these kind of big things that you often hear in the news and stuff like that. Okay. But, you know, this is kind of the number that we're going to work with for today, that, you know, the amount of solar radiation that enters the atmosphere is 342 watts per meter squared. We're going to see how that interacts with, you know, whether, you know, how much radiation the Earth itself emits, what role the atmosphere plays itself, and the different chemical makeups of the air that's around us. But, you know, this is kind of our starting point here. Okay. Okay. Any questions on this? Okay, good. All right, so that's the amount of solar radiation that comes in. You know, the Earth also is going to emit radiation as well, because, you know, the Earth is a big mass that is at a non-zero temperature. Okay. So it's surface of the Earth. Okay, and so this amount, we'll call this E Earth, is on average 390 watts per meter squared. Okay, so if we draw a diagram, right? And so we say this right here is the Earth. Okay. And so on the one hand, we have radiation from the sun coming in, right? So this is GSO, right? We know this 342 watts per meter square, okay? And then coming off the Earth, we have this Earth's emission, okay, which is 390 watts per meter squared. Okay. Now, of course, you know, that depends on where you are in the Earth and kind of your altitude, whether you're on the mountains or not. But on average, you know, across the entire Earth, you know, the Earth is emitting 390 watts per meter square based on its average surface temperature. Okay. Okay. Now you may look at this diagram and you think, great, you know, the Earth is emitting more heat than it's taking in, or maybe you think that's not good. So, you know, we're going to be, we're going to lose a lot of heat. Well, the thing that kind of complicates this is our atmosphere. So, you know, our atmosphere here, you know, it's made up of all different gases, nitrogen, oxygen, carbon dioxide. So that kind of complicates the picture a little bit, because the atmosphere, because it's made of such dense kind of gases, is able to actually absorb a lot of this radiation, both the radiation that's coming in from the sun, as well as the radiation that's coming off of the Earth. So the most common gases that are in our atmosphere, nitrogen and two. We have oxygen, of course, O2. We have water. Water is a big part of our atmosphere as well. We also have O3. So O3 is ozone. when I was a kid, the ozone layer was kind of a big topic of conversation a lot, okay? And of course, CO2, carbon dioxide. And of course, there's other stuff in the air as well, but these are kind of the main players, okay? Okay, so how does that change our balance here? So, let me go ahead and draw our Earth's surface again. Right? And so just like before, we're going to have solar irradiation coming in. So this can be GSO equal to 342 watts per meter square. Okay. And we have the emission from the Earth as well. Okay, so this is 390 watts per meter square. Okay. Right. But the atmosphere is basically it basically separates the surface of the Earth from outer space. And so, there's kind of a big cloud of gases here, which we call the atmosphere. Okay. And so what the atmosphere is going to do is it's going to absorb some of this radiation. So what's going to happen is that a small portion of the solar radiation is going to come in and go to the atmosphere. Okay. Right. And so it's been estimated that about 67 watts per meter square from the sun is absorbed into the atmosphere. Okay. But the main effect that the atmosphere has is that it plays a big role in absorbing a lot of the radiation that the Earth actually gives off. And so actually, this 390, out of that, 350 watts per meter square actually goes into the atmosphere. Okay? And only a very small portion, 40 watts per meter square, only a small portion of the Earth's radiation actually makes it back out to outer space because the atmosphere is kind of in the way. Okay. Okay. And so, from one perspective, you can say that, the atmosphere kind of plays a role in kind of trapping a lot of the radiation that comes in, or a lot of the radiation that comes off the Earth that, should be going to outer space, but the atmosphere is kind of trapped in here. Okay. Which is not a bad thing. All right. And so, a big part of a big consequence of this is that our atmosphere is warm, but that warmth also gives life as well. Right. And so without the atmosphere there, life on Earth would be extremely cold. And so we wouldn't be able to sustain, life as we know it. And so, we do need to retain some heat within the Earth, just so that we can use that energy for our own, to grow plants and to, power our way of life. But, the delicate balance of this, that's kind of the issue. And that's kind of what we're going to talk about next. But, it's important to kind of recognize that the atmosphere plays a very big important role in this atmospheric radiation balance. Okay. All right. Any questions on this so far? Okay. All right. So then what's the main issue here? So, it is very important for the atmosphere to retain and absorb a lot of our radiation. The question is the main issue here is where is that heat? Where is that thermal energy being stored in the atmosphere? Okay, and so, probably, you guys probably grew up with this, but there's always a lot of talk in terms of, the quality of the air and how much carbon we're putting out into the environment and kind of what we do in terms of, human activities, how much we drive, how much we use, how much fossil fuels we burn, right? The main consequence of all this is, how much carbon we put into the air, okay? And so in general, as the amount of CO2 in the environment goes up, okay? Right. That tends to bring the amount of atmosphere down closer to the surface of the Earth. And so that means that as CO2 increases in the atmosphere, then all this absorption and storage of Earth's radiation happens closer to the Earth's surface. Okay. And so what we perceive is as, as beings that live on the surface of the Earth is that we perceive things getting warmer, right? And so we see, things like the ice caps melting, right? We see, temperatures rising and the ocean level is going up. All of that is kind of all consequences of the fact that, Earth's radiation is no longer being absorbed high up in the atmosphere where it doesn't affect us. It's being absorbed much closer to the surface, and that has a lot of consequences in our kind of our natural ecosystems and just kind of our way of life. Right? And so when people talk about the atmospheric radiation balance, ultimately, the conversation kind of comes down to how much CO2, how much carbon is in our atmosphere. And so, of course, there's a lot of research going on nowadays in terms of, how do we deal with this? And so how do we, reduce the amount of carbon we put into the atmosphere? How do we sustain our daily life without, producing so much carbon? Are there ways to take carbon that's in the atmosphere and use it for something useful? A lot of that has to do with this. Okay. Okay, and as engineers, a lot of you will likely go into industries that are going to be focused on, things like this. And so, there's, I think, as time goes on, I think there's always going to be an interest in terms of, protecting the environment, minimizing kind of our human imprint, especially as technologies advance. And so we're kind of at an interesting spot right now where, computing or kind of the amount of computing that we do, with the rise of AI and other techniques is at an all-time high. And so, running those systems, running those servers is not cheap, and so requires a lot of energy. So the question is, I think for the future is, how do we use these technologies, keep advancing, but, still kind of maintaining balance of everything that that we've had before. Okay. All right, any questions on this? Okay, all right, and so that's 407, and so that's everything. And so on Thursday, when we come back, there's gonna be no new information on Thursday. It's our last lecture, so we're just gonna be reviewing. And so keep an eye out. I'll probably send an email this afternoon so you guys can vote on what you want to see on Thursday. Because remember, we're not gonna have time to review absolutely everything, so I want to make sure it's useful for as many people as possible, right? But yeah, thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you on Thursday.
figure it out.
Thanks, guys.
Tried to do it in class.
My grade, so I'm not great.
You know.
It's like, it's super weird. I was trying to figure out the name.
Yeah.
And I was like, oh, which name is it?
I'll probably have office hours on Monday. We'll probably have extra office hours. You guys are fine. But I'll office hours probably Monday morning and Monday afternoon.
What do you think? Past 2 minutes.
Yep. Yep, I would definitely look at the practice finding, the format can be very similar.
I don't know, like, I think we should do it.
Mhm.
Like going over the homework or like-
Yeah, homeworks, I would definitely do all the example problems, so I think there's a couple of examples we didn't get to do, for those who are in the notes. I would definitely look at those, but the problem that's gonna be on the exam is very similar to the one we did today. So I would definitely know how to do.
You know, you don't have to do the final, right? No, you don't have to do it, you just get a 0. I have a question.
Yeah.
So for the homework, I forget if you do it. Drop the lowest
I
one.
do, yeah.
Okay.
It should already be calculated.
Okay, because I'll show you, but for like this last one, like I try to do it before class,
Yeah,
and so. Let me pull it up. For this last, one, I forget why I did this, but before class was trying to do everything. And then for like my Q of E, like you know what to see, I know it's bad. I tried to like add these two together.
Yeah.
And so I don't think that was right, and then.
no, yeah, so actually, so whenever you have a branching path, so we used to do that before, because the heat would always just go in one path.
I see.
But whenever you have a branching path like this, right, and so say you want to go from this node to this node, you
Okay.
can't just sum up these two, because once you're at here, the heat can actually split and go
I
that
see.
way. So that's why when you're doing radiation, I suggest you just do one resistance at a time.
Okay. So this one I would use is if it's just like a completely straight.
Exactly.
Okay. All right then, yeah. So I was heading in the right direction, just not exactly the right way. Okay. I'll have it ready before finals happen. The solution.
So I think homework due this Friday,
Okay.
so I'll probably post it Friday night.
All right. Try not to get too sad when you see my homework. though.
Okay. I don't. Yeah. Yeah. Yes, yes.
So for the final, that you posted.
Yeah.
You had,
No, no, so that's one thing I changed, so. So the thing I added for your guys' final is internal convection. So no heat exchanger, but there is internal convection.
Is there, 3 problems, right?
3 problems, yeah. So well, okay, so the problems are gonna be hybrid, but approximately 1/3 is gonna be conduction, 1/3 convection, and 1/3 radiation. But you can expect to see maybe some problems that are, maybe 30% convection, 70% conduction, but overall, it's gonna be an even split.
Are there ones that you would specifically look at?
Well, the radiation problem, we weren't able to do too much, so I would definitely look at the problem we did today, and the homework is gonna be.
Oh, is there a way I can get my solution? Because I'm taking mine Thursday, so I can use that. for my
Yes,
study.
I will email it to you probably tonight.
Okay, thank you, that'd be great.
It's because my Roman name is late. But. Yeah, I wanted to push.
Circuit that connects those ones.
Yeah, yeah.
A2.
Ah, yeah, oops. Yeah, so it depends on the view factor. So, basically, basically what I look at and see, so if you're gonna use F12, then the area that you multiplied by is always whichever surface is in the first slot. of the view factor. So if we have F12, we're gonna multiply by A1. But remember, because of the reciprocal rule, this is equal to F21, A2. So you can actually use either one. And so as long as, just know that the area that you multiply by is equal to just whatever surface is in the first slot.
Oh, I see. Okay.
Yeah.
So would that be the same for those ones too?
Exactly,
Okay.
yeah. So actually, this resistance is equal to 1/A3, F3, 2.
So it just depends on how you write it, but it's basically like the view factors, just the ones that are connecting.
Exactly.
in the circuit. Okay.
Exactly.
And then for the concept we just went over for like Earth's radiation,
Mhm.
is that gonna be on the exam?
It is, yeah,
Okay. Would it be like more conceptual then?
yeah,
Okay.
conceptual for sure,
Okay.
yeah. There's no problems associated with that. So.
Okay, what was the setup for the final? It was like.
There's gonna be 8 conceptual problems and 3 problem-solving problems.
Okay.
Yeah, so for the 3 problem solving, it's not gonna be, pure conduction, pure convection, well, the radiation is kind of its own thing, but you can expect 1/3 conduction, 1/3 convection, 1/3 radiation. But there may be some hybrid problems where, conduction and convection are kind of combined into one problem.
Okay,
Yeah.
okay, for sure. Thank you.
Yep,